I'm Alex Jopp with Solar Tech Collective, and this is Clamping Down on Solar Hazards, Part 2. In Part 1, we discussed how using a clamp-on ammeter to verify a lack of current is essential to safely working on PV systems, as there are current hazards that exist even in properly installed and operating PV systems. Now we're going to talk about two complex hazards that can emerge on improperly installed or operating PV systems that a clamp-on ammeter can help us to identify and mitigate. Remember, checking the wire may prevent a fire.
Warning, this video is for educational purposes only. Electrical systems contain dangerous voltages that can cause severe injury or death. Installation and maintenance and testing must be performed by qualified persons. Never attempt electrical work without proper training, licensing, and personal protective equipment. Solar Tech Collective assumes no liability for property damage or injury incurred as a result of the information contained in this video.
Reverse polarity, it happens. Let's take a look at some diagrams and think about how your technician's best friend can help you out when you encounter these situations in the field. Reverse polarity is pretty easy to understand. It's when you get your positive and negative wires flip-flopped by accident. The positive and negative home runs of one or more strings are reversed. You can see this on the screen. This positive right here is landed on the negative bus bar, and the negative is landed on the fuse holder that's supposed to be the positive. So we've got our flip-flopped home run wires in this combiner box. This is a really easy installation error to make. I've done it. Everybody I know that I've worked with on sites has done this. We have a lot of wires on PV systems. We have a lot of black wires, and it's unfortunately a very common mistake. That said, this is an easy error to catch during system commissioning with your meter. However, if you don't catch this before you put those fuses in their fuse holders, this is going to be a challenge for you. All right, let's say you are commissioning the system. You have a combiner box, but your fuses are not yet installed. You've got multiple strings. They're about 950 volts and 12 amps short circuit current. We take out our meter. We're going to test our voltage. We've got our positive meter lead on the positive input to the fuse holder. We've got our negative meter lead on the negative bus bar. We don't see any signs of reverse polarity on our meter. 952 volts, we'll call that full array VOC. Looks good. Okay, what happens if we check our VOC on this bottom fuse holder where we have the reversed polarity situation? Our positive meter lead is connected to that negative conductor coming off the string on the fuse holder, and our negative meter lead is connected to the negative bus bar where we have our positive conductor landed. Our meter has a negative sign on it. That's our indication that we have reverse polarity here. Our meter leads are in the right place. They're plugged in properly. Our meter is telling us that we have reverse polarity. Remember, there's no completed circuit here yet. We've got our fuses out. The only potential difference here is from positive to negative of that one string. So at this point, you step back, you think about your standard operating procedures and what to do next. This is a relatively straightforward fix. Of course, the first thing we do before we unplug anything is verify a lack of current with our clamp-on meter. We know how to use it. We're going to use it the right way before we unplug anything. Then we're going to unplug the home runs at the modules. Well, why do we do that? Because we do have voltage. We don't have current flowing, but we have energized circuits that we need to be hyper aware of as we're making changes to fix this system. So we've removed the voltage, and then we can go ahead and rewire this combiner box the right way. Well, what happens if you missed it during commissioning? Somebody was having a bad day. They reversed the polarity on the circuits, and then they put the fuses in before they checked voltage. What happens now? Well, when we check our voltage now, we're going to measure 0 volts DC from those same terminals that we just checked in the previous slide. When we had the fuses out, we're getting a very different reading now. When we had those fuses out, we measured full array VOC. Now we're measuring 0 volts DC. What is happening? Well, now we have a looping short circuit current. We don't have any potential from positive to negative in the circuit because we've got full short circuit current looping around. If you follow the circuit here on the screen, what you'll see is that reverse polarity string is now in series with the quote unquote normal string. So we've got a looping current that's flowing through this circuit. It is a short circuit. Now, fortunately, our PV conductors are sized to handle short circuit current. it's not going to blow the fuse in this situation. The fuses are sized to handle that too. We definitely have a problem, but it's not a problem that's going to start an immediate fire. So yes, we have a problem we need to fix. But before we can fix it, before we open any connector or any fuse holder on a site, we have to check for current with our clamp-on meter. So let's check current here on this positive input to the fuse holder. We would do that before we ever opened this fuse holder. What we'll see is that we've got full looping short circuit current from this rather long string of modules. So you can't open that fuse holder or you're going to draw an arc and probably catch that combiner box on fire. All right, let's check down on the bottom. Maybe we'll get a different reading on this fuse holder that's also connected to this string. Nope, we're still going to get 12 amps DC, same circuit, same short circuit current flowing through these wires and through the fuse holders and through the bus in this loop. All right, one last check here. What do we get if we measure current on those conductors that are connected to the negative bus bar? Maybe we can lift those screwed terminations. So you see our meter reads 0 amps DC. Well, not so fast. There's only 0 amps because we've got two conductors in the circuit at the same time that are canceling out the current that the meter is reading. So that's operator error. We can't pull either of those conductors off their termination. We cannot open either of these fuse holders. So what do you do now? You've got looping short circuit current flowing through these modules and through this combiner box. This is why we have standard operating procedures. Your company and your crew need to decide how you're going to deal with this situation. I've got some ideas. You could turn off the sun. You know, and I don't mean that facetiously. You could wait until nighttime if that's a possibility for your crew. At that point, you'll have basically 0 current and 0 voltage, and you can safely fix the system. You could also sacrifice your linesman's pliers. While I will say that this is a common response in the field, it has to be done very cautiously and thoughtfully. You need to make sure you've got a fire extinguisher on hand, you're wearing the right PPE, you need to make sure that however you do this, you're going to be able to fix the problem that you caused when you cut through a wire. Once you cut through the wire, you no longer have short circuit current, but you definitely have voltage. At that point, you can start figuring out where to open connectors that don't have any current flowing on them, and you can resolve the situation. Honestly, this is probably the most common response in this scenario. Maybe you cut a conductor at a point where you've got enough wire to pull it back into the combiner box. Maybe you cut a conductor where you can recrimp on a connector. Again, standard operating procedures are important to know how to deal with this situation safely when you encounter it on a site.
Well, if you spent any amount of time measuring the open circuit voltage of strings of PV modules in the field, it's not going to be a newsflash to you. String voltage varies even when you have the same number of the same modules in series. Modules themselves vary a little bit. Installation errors happen sometimes. Everything's supposed to be strings of 18. Well, we got some of 17 and some of 19. Whoops. Sometimes modules fail and degrade over time. They may lose voltage. Some may lose it faster than others. And bypass diodes can also fail over time. All of these differences in voltage lead to what we would call a string voltage mismatch. It can be pretty minor, maybe a volt or two if everything's good. But if we have some issues that we just talked about here, that voltage difference can become pretty significant. And we'll take a look at what that can cause and how you might be able to catch it and prevent an issue with your clamp-on meter. Take a look at what happens when a system's operating and it has strings that have different voltages. So mismatched string voltage, and we're really talking about strings in parallel here. Right? So we have modules connected in series to form a string, and then we connect strings in parallel either in an inverter or in a combiner box to increase the current and thus the output power at the same voltage. So when we have those parallel strings and they have different voltages, they're going to operate a little bit off of their true maximum power voltage. That means they're also going to operate a little bit off of their true maximum power point. So this is going to result in a little bit of lost production. Maybe so little that it just appears like noise and we don't really notice it in terms of system operation unless we have some pretty good granularity on our data acquisition system. Okay, let's take a look at this by turning to our good friend, the IV curve. And here we've got a graph showing two strings and then putting those two strings into parallel. String number 1 in blue has an open circuit voltage where it hits the x-axis of about 850 volts. String number 2, for whatever reason, maybe there's a couple of modules missing from it, maybe there's some modules that have been damaged or degraded over time, it has a lower voltage of 750 volts. Both of these strings make about 12 amps. You can see where it hits the y-axis, the current axis, about 12 amps. That's the same. The difference is the amount of voltage they can make. So what happens when we put these strings in parallel? We know that when we put strings in parallel, the current is additive. So the new IV curve that is going to be formed is going to look like the green curve, the two strings worth of current added together, 24 amps. But you can see that the voltage at the knee of that IV curve, it's not really ideal for either one of those strings. If you trace that down, it looks like we're probably somewhere in the neighborhood of, let's say, it's right about 700 volts. So it's a little bit higher than the maximum power voltage of the orange string, which is maybe 675 volts. It's a good bit lower than the true maximum power voltage of the blue string, which is maybe 775 volts. So we're losing a little bit from each one of those. Again, it might not be a huge production loss, might not really even be noticeable. The question is, what happens when we are not operating that system and there's sunlight on the array? Well, what I'm going to tell you is that's a potential problem due to that mismatched string voltage. Now, when I say not operating, it could mean the inverter's off. The sun's out and the inverter's off. It could be that a combiner box where these mismatched strings are connected in parallel is disconnected from the inverter, so there's nowhere for it to send its current. Or it could even mean that the utility grid is down. Whatever it is, something is causing the system to not be able to operate during the daytime when it normally should, and that's where we can have an issue. Now, what's going to happen when the system is not operating, but there's a radiance on the array, is the higher voltage string or strings are going to backfeed into the lower voltage strings. Remember, when we have circuits in parallel, the voltage is going to be the same everywhere throughout all of those circuits. And so what we're going to find that's going to happen is we're going to get to a point pretty close to the maximum power voltage of this higher voltage string. That voltage is going to basically become the steady state voltage for the overall array. That happens on this lower voltage string at a negative current value. We're below the x-axis. That IV curve, we don't usually talk about it, but it extends down into this negative current range. And we are going to pick a voltage where we come to a steady state, and that's going to mean pushing current from the blue string into the orange string, right? You can see we're below the x-axis. We're putting about 12, 13 amps into that string, backfeeding it into there. Now, this probably isn't going to be a huge issue if I just have two strings in parallel, right? The amount of backfeed current that one can send into the other is going to be probably about the amount of current that other string can handle. So there's not going to be enough current to damage things. When we have more than two strings in parallel, whether that's on an MPPT input in an inverter, or if it's on a combiner box where we may have a lot of strings in parallel, well, this can result in very rapid overheating of the lower voltage strings. I've seen modules get cooking hot when this happens. Again, it's due to that voltage difference. When the system is off, higher voltage, it's going to backfeed through that lower voltage string to get to the other side of the circuit. This could result in a thermal event. I've seen models get hot enough where they have started to damage the batch sheet, and, now we've got problems. Okay, let's tie this back into one of our favorite uses of our clamp-on ammeter. That's right, verifying a lack of current before opening a non-load break rated device, like the fuse holders in this combiner box. If you've done much of this, you may be wondering, why do I hardly ever get a 0 when I'm trying to do this on a system that doesn't have any issues and when I'm using the meter correctly, meaning I zeroed it out? Well, it's the same concept. We're going to have a stable bus voltage, and that means even small differences in voltage between strings that are in parallel will cause current to flow. You might be able to see on the meter on the slide here, we've got 0.2 of an amp. So not 0, it's pretty low. The question is, what do we do when we don't have that 0? What if there's just a little? Well, first off, if you've looked at your clamp-on ammeter, you may notice that there's an arrow marked somewhere on the jaws. That's going to show you directional flow of DC current, and you can literally see which strings are feeding and which strings are being fed. That would be which strings are the higher voltage strings and which ones are the lower voltage strings. We can then go ahead and potentially isolate strings that are putting out the least amount of current. Get those ones out of the picture. That's going to reduce the overall current into the worst strings, and hopefully we can bring that down to an acceptable level close to zero. What is that level? Well, what are you going to do? You're going to refer to your standard operating procedure to determine when a little is a little enough. So a big takeaway here is if there's current flowing on DC circuits when the system is off, there's either a short circuit with reverse polarity, as we talked about earlier, or there is a string voltage mismatch causing backfeed to occur. Either one of those can be a hazardous situation. What are we going to do? We're going to always be checking current. We're going to pull out a clamp-on meter. We're going to make sure there's not current where it shouldn't be. We're going to make sure that there is no current when we expect there to be no current. And it's going to make us a safer and a better technician out in the field.
Thanks for watching. There are 2 other videos in this series. Click to check them out and subscribe for the latest on electrotech.